Hi, everybody. Hi again. We're going to get started. One quick question. There's maybe one or two people who didn't want to be photographed, and there's a little sticker on. And for our photographer, he would like to know who that is so that he makes a specific attempt to avoid photographing that person. So if you're here, if you could raise your hand or stand up. No? Okay. That person has left. So, okay. Maybe they left with the laptops. So that's but the person didn't want to be photographed. Okay, so well, hi again. So I'm Justin. This is
Hey, I'm Guillaume.
and we work in SRE at Criteo, and we focus on data processing. And today we're going to talk a little bit about what we've been working on over the past 9 months or so, which is thank you. Which is about how we think we can make building large-scale batch data processing pipelines a lot easier by taking another look at SQL. This is going to be a bit of a storytelling process because this is a little bit of our analysis based off of our learnings since the team sort of got started about about 7 years ago, almost to the day actually. So without further ado, so the agenda here is we're going to do a little brief recap to talk about data engineering and what it actually is. We're going to talk about imperative aspects of data engineering, which you might be surprised to find out we're still doing sort of everywhere. And then we're going to switch to talking about how we can make everything declarative and we can delegate a lot of decision making to the runtime. And then we'll talk about a demo. We're not going to do a demo here, but there's a little joke there. And we're going to talk a little bit about how we're tackling that here at Criteo. So also, a lot of people here, I guess, know a little bit about the scale at Criteo. So we've pulled out the slides about all the big data numbers and all that other stuff. But one thing that I think is important to remember is that the scale at an organization like Criteo isn't just in the volume of data, it's in the volume and variety of people working on the system and contributing code into production. And at Criteo, we have about 1,000 people who at any given point in time can contribute code to data pipelines in production at a very large scale. So that's also a different constraint that we have that maybe some other companies don't, but also other companies do, like Spotify and you know, the Googles and whatnot of the world. So, okay. So let's try to define data engineering for a second. It's funny, if you type what is data engineering or define data engineering into Google, it actually sort of splits across two definitions. One is basically sort of data science-y people who are going to build data pipelines and produce data, or actually data systems engineers. And the data systems engineers are the folks who try to build the platforms like what we do and what Lynn and Fallon talked about earlier, sort of the infrastructure engineering side of things. The thing that isn't actually talked about a lot when you look that up is why do we do it, right? So what do we, we're doing data engineering. Why are we doing it? We're doing it to actually try to get information either out of the system or to actually put it back in. And when we get it out, we sort of call that, in classical terms, BI, so business intelligence. We're trying to understand what happened to maybe make better decisions going forward. And I like to say that when we try to put intelligence back into the system, that's closer to AI or machine learning, where you're going to try to, look at the past history, come up with a model, put it back online, and then have your online engine do more intelligent things. So you're injecting intelligence back into the system. I think at this point in time, conferences like this, which is a very small conference, but then also very big conferences with thousands of people, wouldn't exist if this weren't to some degree difficult, right? So that's data engineering, right? Now what's big data? So data engineering can happen really at any scale. So what about big data? Well, historically, big data was defined by the 3 V's, velocity, volume, and variety. Velocity is how fast the data arrives. Volume is how much you've got sitting out somewhere that you might need to process at some point. And variety is in different structures of data, basically. So you have JSON data, you have protobuf data, you have completely unstructured data, like you're parsing web pages like Google or whatever, right? That's a variety of data topics, and that's sort of the characteristics of what's coming into the system. But then there's also we conflate the idea now of big data with data science. And so data science can happen sort of at any scale, and with the power in today's laptops, as well as some of these new multiprocessor machines that are coming out with terabytes of memory, you can actually do quite a lot of scale up, which would historically have been a distributed problem. And people oftentimes think, well, there's terabytes of data, so that's big data, and I'm doing data science on big data, but it's actually on a single machine. So big data is a little bit conflated between the classical definition and then, hey, I'm doing these hard algorithms, and that's big data too. And also, again, big data, same story. Typically, it's considered to be at least somewhat complicated. Okay, so one more definition, and then I'll quickly stop with the scholastic aspects. So what about data processing pipelines? So as was referenced earlier, a data processing pipeline is basically a directed acyclic graph of various sorts of computations, right? Some of those computations are going to read data, some of those computations are going to transform that data, and some of those computations are actually going to send that back out to disk somewhere or downstream to some other job. I sort of think that data engineering became a term because of the data pipeline side of things. Doing a single unit of work is and has been to some degree trivial. Doing that repeatedly at scale, up to date, with low latency, that's kind of hard, right? And especially when you have a bunch of these things that need to be executed exactly at the right moment, with exactly the right inputs, with a bunch of semantics that are all well understood by the consumers of the data, the producers of the data, and so forth. Okay, so big joke. This is all just ETL. We've been doing this since 1995 or whatever. Whenever the first sort of business intelligence tools were written, this is all reading data is extraction, transformation as well transformation, and writing data out is loading data into some other system, right? So this is really just ETL, and in fact, and so pipelines are basically just ETLs composed with ETLs composed with ETLs composed with ETLs. A MapReduce job, an Apache Beam job, that's an ETL. A bunch of Apache Beam jobs or Spark jobs is just a bigger ETL. And the thing about the transformations is that those transformations can be as trivial or as complex as we want them to be. When we think about data science and machine learning is actually just ETL as well, right? The transformation is just a little bit more complicated than maybe doing a join or a group by. Okay, that's it on definitions. So let's talk about imperative data pipelines themselves, right? So, okay. Who has an idea of what we might be talking about when we're talking about an imperative data pipeline? Maybe an imperative algorithm. Anybody? Okay, yeah, Alexandre, thank you. Well, so this is what is sort of a stereotypical imperative data transformation. So this is a very, very, very fragile script that's going to read a bunch of data. It's going to parse it in a particular way. It's CSV data. Hang on. Okay, there we go. So basically, we're reading data from standard in. We've got some nice, very robust regex-based parsing here, and we're splitting out some data into some very well-named variables. And we're doing some nice little transformation. We're doing some type coercion here, basically, and further type coercing into something we want. And then we're starting to do some aggregations, right, into some nice hash maps. And then we're going to go ahead and iterate over all that and spit out basically some groupings. So this is extremely imperative. I'm telling the computer exactly what to do, right? It's to do this. I want to know the number of clicks per hour and the number of individual clickers per hour. And this is exactly how you're going to execute it. Okay, so how do we turn that into an actual, so this is just a transformation, right? The input comes from standard in, and the output goes to standard out. So this by itself is sort of doing nothing. So we need to stitch it together into a workflow. And so now we have an ETL. So here we have a nice little ETL. We've got, we're copying some data from some random host. in a well-known format. And then we're uncompressing it. We're catting that through, or piping that through our little transformation script that we just wrote. And then now in this case, we're going to chain it through some script I didn't talk about, which is not written, but basically is maybe loading that somewhere, say into a database. And then we've got a little DAG here, so it doesn't fork out or anything, but that is a DAG. So this is an imperative system that's actually correct and it works nicely. And if you're like me and you've been around the block a few times, this might feel really good because it's all command liney, it's Unixy. I can sort of understand it. I can grep logs. I can add little debugging in when I need to. It's really easy. It's like good home cooking. On the other hand, we've already identified that it's fragile, right? The parsing in that Perl script was really awful. What happens if somebody adds a field or reorders things, right? The data comes in slightly differently. Well, our whole thing is broken, right? That script that I showed was actually pretty trivial. I think probably anybody in this room could understand what was going on in there if they looked at it, for more than 5 seconds. But as we know, when we're in the real world and the data is actually messy, those scripts get very, very, very nasty, right? And it gets very, very hard to read. And usually only the person who wrote it can really understand it. And maybe only when they wrote it, right? You go back to that thing like 6 months later, like I have no idea what I was doing. What is this, And you have to go back and debug everything to understand actually the transformation and go find the bug that you were thinking about. And then obviously that's a completely single-threaded algorithm that I showed. And so if you want to distribute that, you're even multi-threaded on a single machine, you're gonna have a hard time, right? And so this is exactly where we come to with sort of the big data wall, right? Our little imperative world was just wonderful when everything could be processed in reasonable wall clock time in a single thread. Like life was great, everything was simple, nobody cried. And then now we get to the big data problem where that's just simply not gonna do. Nothing can keep up anymore. This is where the volume problem comes in, and we really have to figure out how to distribute this computation. And so once we start distributing things and things are no longer executing locally, right? Or we can't actually execute the code locally to debug it. We can't take a small subset of the data, copy it over to our machine and sort of rewire that little iterative pipeline that I showed you and run it locally and then add our little print lines or whatever sort of debugging flags we want to include. We can't do that. We just can't do it anymore. It's running off on some distant machine. We're gonna have a hard time hooking up a remote debugger to it because there are these like sort of transient jobs, and getting the logs is hard. You need a whole bunch of plumbing to make that work right? And that's why we end up having to start thinking about things a little bit differently. Also, to go from that nice single-threaded algorithm where I'm just accumulating stuff in a hash map locally in that process, to the point where I can distribute that out, well, now I have to sort of re-implement MapReduce, right? I have to figure out how to distribute that computation in a way that's going to give me correct semantics on the way out. And it becomes basically pretty complicated and costly to maintain and operate going forward if you stick with this sort of imperative worldview. So that's the other problem. So that's the big data problem. And then we have the other aspect of the scale, which is the team size, which I touched upon at the beginning. When you're just you and your friends, in a garage doing your little startup, it's all great, right? Because, there's the person who's charged with doing all the data pipelines, and whenever we need to add a feature into it, we just talk to that person, and, she gets that thing, bolted on, and everybody's happy, and she reruns everything that needs to be rerun, and everybody understands what's going on. When you're in a geographically distributed organization with thousands of contributors, that no longer works, right? Now you start having to think about your data sets that you're producing as services, right? And there's service boundaries, and there's schemas, and there's all kinds of things. There's many contributors to that data set potentially, because everybody wants to get their little data feature into it, especially if we're talking about machine learning models. Somebody wants the weather in their model. Okay, well, you have to stitch that through 15 different jobs and across 3 different teams, and those 3 different teams don't really care about your weather problem. They just care about making their thing up and running for their primary purpose. So you have to sort of convince them, and in this case we need to start caring about things like lineage, where's the data coming from, who are my consumers, and a central catalog so that people can easily bolt on their jobs to consume that data without having to rewrite, how the data gets serialized off disk. You don't want to think about that. You want that to be provided for you, and so on and so forth. So what we've talked about now is we went from this little localized world, we're all working in our garage and everybody knows everybody, and there's a single person or maybe a single small team responsible for all the data production, and everybody implicitly knows how everything works in a nice little scale-up, single-threaded world into a big sort of distributed problem, not just distributed in terms of volume and compute, but in terms of distributed across people. And so really what we start needing to think about is how we build a platform. And so with that, I'm going to hand it off to Guillaume because he's smarter than me and he's going to tell you how we build a platform out of this.
Okay. So yes, we were coming from this world. So yeah, at the beginning of the team, when Criteo was smaller and the team was very small, we were building the data pipeline ourselves, the data processing ourselves, and we were building tool to be able to do that efficiently and quickly. And at some point, when more people needed to create data at Criteo, they started using our own tool. And our tools were a bit complex, so we started to try to abstract them and to make them easier to use. But at some point, we ended with some hundred of data pipeline owned by different teams at Criteo, all using our tool, and we were kind of responsible for this tooling. So every changes needed to the tool or to the library was requiring a lot of synchronization over the company with all this team. So we decided that it was not working anymore at this scale, and we needed a real platform. So how do we define the platform here? Yeah, we really want to inverse the control. So we want to be owner of a platform where people can ask us to transform data by providing us a description of the transformation. So we don't provide the technical tool anymore and they use it to do the transformation themselves, but we own the platform, we own the technical tool, and we want them to explain us how to transform the data to create a new data set. And we need to do that, we need a way for them to express how to transform the data. It needs to be powerful enough, so it's not, it can work for real world case scenario. But it has to abstract all the technical, low-level technical implementation detail, so we can have some flexibility about the way we will actually run the transformation, and we can change our tool or make some evolution on our platform. So for that, we decided to use SQL. Because SQL is a really nice way to express a transformation. So a lot of people are seeing SQL as a SQL query as a way to query some data. So extracting some data from a data warehouse and summarizing it. But it's actually, querying a data is actually just transforming some data. Most of the time, you ask for a smaller representation of your data, but you can as well ask for as big version of your data, but just another view of your data. You can combine two columns, add a new column, remove some rows, but it's not necessarily a query itself. It can be a transformation. And so this is a Hive query. We are starting to use a lot of Hive query to the transformation. So this one just aggregate some rows and count the number of clicks by day and by hour. And we have a lot of data transformation like that at Criteo based on Hive. Also, SQL comes with a lot of advantages. Any SQL system comes with a catalog, a schema, everything needed. As soon as you start creating your own data engineering framework, you start by defining your own catalog because it's needed for your client to be able to express the data transformation. So you start by recreating a catalog, recreating, a data set, data frame, depends how you name it, but you have to do that. And any SQL system comes with that from the beginning, so it's way simpler. Also, the code, the transformation you can express in SQL is kind of limited because you have to use the built-in SQL expression that is available in your dialect, and you can kind of extend it by creating your own user-defined function, but it's it's a more difficult process. You have to think about it, to deploy it. So it's not as easy as writing some random closure in Scala or Python and sending it to the cluster, because this closure perhaps it hides some complexity or some bug, which is more difficult for us to handle. Also, the governance is more easier for us because SQL is kind of statically analyzable. At the contrary, if we take a bunch of Python or Scala source code file, it's difficult for us to statically analyze them in a build system, for example, and discover what are the real dependency between all these transformations. The actual code can be as complex as people want, and it's very difficult for a system to statically analyzing it completely. While in SQL we are able to do that because SQL is very simple, it's very expressive. But even if most of the transformation were done in SQL, in the declarative transformation model, the ETL itself, the data pipeline itself, was still imperative, meaning that you had all this transformation, but the way you were running them was very imperative. You were saying your scheduler basically runs that, then runs this query, then runs this query. And that's exactly the kind of operator you have in Apache Airflow by calling the upstream job for each job, and we have our own Airflow-like scheduler called Cuttle at Criteo, but it's basically the same, where you explicitly expose the dependency between your job. And actually, if you look at a query, this dependency is already present in the SQL transformation. Because in the SQL transformation, you have this from clause where you say from which table, so from which data set you want to read some data, and you have all these predicates that exactly say from which part of your data set you want to read some data. You have some filter, or you have some join predicates that already indicate that. And this dependency is very difficult to manage like this. So at first it looks really simple to write this set upstream and depends on when you are creating your scheduler. But this is some real world code at Criteo, and this is a real dependency between a set of jobs. And as you see, it's become impossible to track, especially because it can be not completely accurate regarding what is in the SQL query itself. A query itself can, for example, define a different offset here. I mean, in the scheduling, you declare an offset, but the query itself, it could read a different set of data. It should be the same, but perhaps it's different because both have evolved and they are not the same anymore. So what we wanted to do is take all these SQL query we have and schedule them automatically by just analyzing them and run them. And it's actually very close to, we discovered that it's very close to creating a build system actually, because you are basically building some data. So for the model, how do we incrementally build some data? Because we are using Hive, and this is a very common pattern, we have this notion of partition dataset. So dataset can be non-partition, meaning that they are built at once. That's typically the case for dimension, for example. So they are computed at once, they are written at once. And some are partition, meaning that they are incrementally built by adding some partition. And you can also remove some partition to delete some data. And the way to modify the data is basically to delete a partition and to recreate a partition. This is very common. Not all systems have a real implementation of partition. Sometimes they just call that table, and then you can select several tables at once. But for example, in Hive, they have this table and partition. And because we are using Hive and Presto, they both share the same model. So we are using that. So for example, this fact hourly click table is actually a partition table. So the day hour column are the partition column, meaning that you can insert some data in this data set by creating a new day hour tuple. And so physically, it will basically create a directory on HDFS for us. And so that's the way you incrementally build the data set. But what we're missing in the Hive SQL language were a way to declare the dataset, the partitions themselves. So you can declare the partition column. You can say in Hive, okay, there is this day column and hour column, and there are both partition column, but the system doesn't know what should exist for this day and day and hour partition values. It has no ID. As a human, when you read that and you see day and hour, okay, you have the ID that it should exist for every hour of the calendar, but the system doesn't know that formally, so statically. So we add this idea of extending a bit the Hive SQL query by adding this for comprehension. This is basically a generator. You have that in JavaScript or in Python, and that's the idea of lazily generating some data. And so we just added a bunch of, this is basically the data transformation, which is the actual Hive query, and we added some metadata to name the dataset, to give it a name, to declare the partition, to enumerate all the partitions that should exist. We try to reuse as much as possible some Hive native expression, but we added some new expression that doesn't exist in Hive. For example, this time series stuff that infinitely generates some timestamp based on a cron expression. The cron expression here is hourly, but you can actually put any cron expression you want, and this is the retention, because the stream cannot be infinite in the past, because at some point we have to delete some data because we are in real world. So we set a retention. And yeah, here we are declaring the partition column. So we basically added this part to Hive SQL, and it allows us to automatically schedule all these queries. So just by adding this small metadata on top of each SQL query we have, we can now create an algorithm that allows us to automatically build all the data. So how it works? We look at each query individually. And so you get a query, you compute the set of partitions that must exist right now. So this is because by evaluating that, and that depends of T, it depends of the workload time basically, you get a list of partitions that should exist now. So some will appear while time is passing, and some will disappearing because you have some retention. And so you compare with the reality, what partition exists on the cluster. So you look at your Hadoop cluster and you discover what partitions are there, what partitions are missing, compared to the static definition you have. And then for each missing partition, you look at the dependency of your query, and you see if the dependency are there already or not. If they are there, you can just run the query to compute the new partition. Otherwise, you just do nothing and you wait. And so how do you compute the dependency for the query if you don't declare it using Apache Airflow, set upstream, or Cuttle depends on? But actually, as I said, it's already there in the query. So for example, if I take this part of the query, I see that it depends from this other table, below click, and it does not depend of the whole table, because the table below click is basically infinite, because it's an incrementally built data set, so it will never complete. But it needs a small part of this dataset, which is explained here in this predicate. So it needs basically one partition, the same day and same hour as me. And so this is how the system automatically infers the dependency from the query without you having to repeat that in another language, Python or Scala. And you can do some very sophisticated partitioning scheme. For example, and this is real world at Criteo. We have this China region that we open at some point and we remove at some point. And for example, here in this enumerator, in the generator, we can statically declare this. So one partition China appear at some point in the past and disappears then, and it's statically explained in the data definition actually. So when you look at the data, you know if one partition is missing and not, because today when you just look at the data, you see that at some point you had this China region and then it disappears. Is it okay or not? You don't know. There is no definition for that anywhere. And now it's now in the data transformation itself. And yeah, so it will basically sometimes in the past generate this part of the partition and then it will forget it later. And so that's basically the idea of automatically scheduling some SQL query, but we are aware that not everything can be done in SQL. I mean, we try to push as much as possible SQL for data transformation because we think it's a great way, but sometimes it's not possible, especially for data science. And so we have an escape where you can provide your own what we call FTI, so for foreign transformation interface. And basically, we have this operator like run Python that are actually user table defined function. So this is a function that can replace a table in the query. And I don't know why. And so this run Python will basically run Apex file. So this is basically a Python program, so it will download it. So our system, when it sees this run Python, of course, it doesn't work, this run Python on Hive. If you try to run that on Hive, you will get a syntax error because it doesn't exist. But our system will pre-process the query and say, okay, we need that, so we'll allocate a yarn container, download this specs file, and run this Python program on the container. And at the end, the Python program is expected to generate some Parquet file, and the Parquet file will be injected as a temporary table that will replace in this query, and then we will run Hive on top of that. So it allows you to, when you cannot do something in SQL, to add more steps, either in Scala, in Spark, or in Python, by providing your own programs that will be run before the query, basically. And they're actually composed because it's just a SQL. You can actually join one output of one Python job with the output of one Scala job if you want, or you can post-process this by filtering in SQL in Hive the result. I mean, it's very composable. You can use it the way you want. It's very flexible. Of course, here, because we don't have the type for the Python program, you have to explicitly say the expected result schema for the Python program. So you say that explicitly, and at runtime it can fail. Like it's kind of a dynamic. This part is not checked at compile time, of course. At runtime, if your Python program does not generate this kind of data, it will fail. It will be a failure. Yeah. And so, yeah, your Python program probably needs some input data as well, because perhaps it's a machine learning model, it needs some data, and you will express this data as a data file operator where you use SQL to select some data existing on the platform. And this will automatically compute the dependency as before. I mean, this part basically explains the dependency needed for running the Python program. So it will wait until the glue billable click table has this partition available before running your Python script because it needed. So that's automatically done for you. And so what is the life cycle? We try to have a life cycle very close to what we are doing in our day-to-day software development and software engineering practices that we have at Criteo. So we wanted to be exactly the same. You write your SQL query locally on your laptop. We provide you with a set of tools. So we have a CLI where you can, for example, run a check to check the syntax error, or dry run to run it in a isolated environment. And we also have a Visual Studio Code extension, so you can visually autocomplete stuff like that. And when you are happy with that, you send it to Git Gerrit, which is the tool we are using at Criteo to do code review, basically. So I don't know if you know Gerrit, it comes from Google. So you commit that. QA bot, which is our CI/CD bot, will basically run a bunch of static check to see if first your query is valid statically, and if your dependency are correct, or if you are breaking something in the graph, and then it will give you a +1 or -1. Then a human will look at your code, can ask for functional tests, so we call that non-regression testing. We will run the query, compare the result with the actual production, and we don't expect them to be the same, because if it's the same, there is no point changing the query, but you expect them to be a bit different, and the report you get will give you the statistics about the difference. Perhaps you are more or null, perhaps you are distinct on a column, and so this is the report you will look at and decide if it's okay or not for you. And so human will give a +2 or -1 or -2, and then you can continue the review process. And when you are happy with that, it will be merged automatically par our continuous deployment system, and it will go in production automatically. So this is very close to the way we develop any other component at Criteo, apart that this is for data. Yeah. And yeah, so this was the idea of the system we had at the beginning, and we implemented it as something we call big data flow internally. And we will do a small demo this afternoon at 5:30 if you want in Club 32. So if you want to see it really and how we implemented it, you are welcome, and we'll do a demo of it. Thank you.